What I want to talk to you now about is fast radio bursts, triggers, and MeerTRAP. And Rob gave a nice little bit of introduction to this already, and I'll hopefully go into a bit more detail. So, as I understand it, there's people in the field, in the room there, who probably are not as familiar with the what fast radio bursts are, and so I'll just start with a little bit of history. The first fast radio burst was the so-called Lorimer burst. It was discovered in archival data that was analyzed while searching for pulsars, actually, in the Small Magellanic Cloud, and suddenly a very bright pulse was detected with the Parkes telescope. And Rob showed this a version of this picture that you can see here, which shows that this pulse was dispersed. And just for those who are unfamiliar with the concept, so dispersion is something that the radio waves propagating through the interstellar medium are affected by. So they interact with the free electrons in the interstellar medium, and these free electrons cause the radio waves to be delayed, so that lower frequencies arrive later than the higher frequencies. And what you can see on the right-hand side here is a map of the distribution of these free electrons in our galaxy, made by Yang et al. In 2016, which gives you an idea of where predominantly we expect to see most of the electrons. And the interesting thing about the Lorimer burst was that it was seen in the direction, as I said, of the Magellanic Clouds. And I have no idea whether my mouse is showing here, but you can see that that is well away from the galactic plane, and we would expect to have a dispersion measure of around about 50 in the appropriate units, whereas the fast radio burst detected by Lorimer had a dispersion measure of well over 350. And so this led to speculation at that time that this burst was not only not in our galaxy, nor was it in the Magellanic Clouds, but it was, in fact, extragalactic. It then took a few years before the community were convinced that these were a astrophysical source, and it was only when a student of mine detected 4 more of these as part of the High Time Resolution Universe Survey project that a population was identified, and so they were seen as the population we now know of as fast radio bursts. So just to drive home this point again, here is a little cartoon that sort of tries to capture what happens. On the far right-hand side, you can see your telescope detecting an object, and it has a dispersion measure of 944 in these units. And you can see that we show the Milky Way here is this, we model it just here very simply and say that approximately there are 30 units of dispersion measure in the direction of this source. And the point is that you can, if the fast radio burst happens, say, in the core or in the center of this host galaxy, then there could be up to 700 units of this dispersion measure coming from that host galaxy. But even in that case, because of the influence of the redshift on the emitted frequency versus the received frequency, it still places the source at around about a redshift of 0.6, or around about 2.2 gigaparsecs away. Of course, what we don't know is where exactly these bursts are taking place unless we can find their host galaxy. So it could in fact be much further out in the edges of the galaxy, and then the contribution to the dispersion measure is much less, and then the source is at a much higher redshift. What's of also particular interest is what is in the intervening medium, so the circumgalactic medium of other galaxies that lie along the line of sight. And of course, famously, the missing baryons. And in fact, through work by J.P. McQuart and his team, they have managed to confirm that most of the missing baryons, if not all of the missing baryons, are in the intergalactic medium. So just to summarize something which I could spend hours telling you all about. FRBs in a nutshell, they are short duration bursts, usually just a millisecond or so of radio emission. As Rob alluded to, they're very energetic for radio events. I understand that you know, when the theorists are always asking us where is the rest of the energy when they talk about the origins of these fast radio bursts. And so far they've been seen in galaxies with redshifts between 0.03 and 0.66. That's not to say that there aren't higher implied redshift FRBs, but so far their host galaxies have not been identified. There are around about 5,000 of these events per sky per day, and so far around 4% of FRBs repeat. But in no FRB have we seen a strict periodicity yet. Some do show very long-term periodicities, and that may imply that they are the origin of the source of the FRBs is in a binary system. They've been detected all the way from 110 megahertz all the way up to 8 gigahertz so far, and not yet definitively seen at wavelengths other than radio, and no statistically significant confirmed counterpart yet. So since the discovery of FRBs, basically every radio telescope in the world has either been following these things up or converted to follow these things up, or even been actually built just to observe these things. And I don't have enough time to tell you about all of these interesting projects, just to point you to some particular interesting ones, which would be CHIME, DSA, and ASCAP in particular. So this is a snapshot probably from a few days ago, so already very much out of date, of the known FRBs and where they are in the sky. Now this distribution is heavily biased by the CHIME project, which is located in Canada, and so it sees predominantly the Northern Hemisphere, and so you can see where all those FRBs from the CHIME project are located. So what are the models of fast radio bursts? So far, you can probably break them down into two main options. They are magnetospheric, so assuming that you've got some sort of magnetized object, like a neutron star, for example, or they are shockwave models associated with some sort of event. And so we can then break these things down again into magnetars, pulsars, white dwarfs, or compact object mergers. And who's to say that perhaps more than one of these mechanisms is actually in operation, and that may be why we are seeing at least two different classes. So magnetars, we can get young magnetars from superluminous supernovae or core collapse supernovae, or even from double neutron star mergers. The pulsar giant flares or giant pulses are sometimes invoked, and perhaps young supernova remnant pulsars as well through shockwave models. White dwarf mergers might be a possible origin, or indeed accretion-induced collapse of a white dwarf. And then all possible merger scenarios have been proposed as an origin for a fast radio burst. So I already alluded to this before, that fast radio bursts are excellent cosmological probes. We know that we can see them at least out to redshift 1 or 2, and there's no reason why we can't see them beyond that. We can use them to measure the missing baryonic matter in the universe, and this is going to be also an important parameter in galaxy formation and feedback models, also looking at the CGM. And we can also look for inhomogeneities in the CGM, including not just the electron density, but also the magnetic fields. We can do eventually tomographic reconstruction of the cosmic web. We've done some simulations which show that if you can find sufficiently large numbers of high redshift FRBs, we can determine the epoch of helium reionization. There's options to look at H0 tension, and also it's expected that at least some of these bursts should be lensed. So one of the keys to doing this is being able to localize your fast radio bursts. So CHIME has been doing an amazing job of finding lots of them, but has relatively poor angular resolution, and they're addressing that by implementing these CHIME outriggers. But localization is really key, and you can just see an example of this here, where we show you the MeerKAT incoherent beam, which Rob mentioned already, or primary beam, to use the imaging term. And you can also see, for example, the moon here, and then the Hubble Ultra Deep Field shown all to scale. And of course, we all know that there are lots and lots of galaxies in the Hubble Ultra Deep Field. And so if you localize your fast radio burst only 2 arc-minutes, then you can relatively poor idea about which of those galaxies is likely to be the host, even if you do a bit of a redshift cut by making some assumption about what the McQuark relation is telling us. If you can get down to, say, an arc-second resolution, like we can with MeerKAT, for example, then for a galaxy like this, we can localize it to saying that it occurred in a spiral arm, or perhaps it occurred more towards the center of the galaxy. And that can be very useful in trying to understand the progenitors of these objects. So far, this has been done for around about 20 galaxies, where host galaxies have been found. And these have been a mixture of the repeating fast radio bursts, because the repeating fast radio bursts offer you an opportunity to go back and look at the source with an interferometer, or even do VLBI observations and get very, very accurate localizations. And through work being done by the PRECISE project, for example. And with ASCAP, they've been able to detect one-time bursts and localize them. And as I'll show you later on, we're starting to be able to do that with the MeerTRAP project as well. So far, from this paper from Bandari et al. In 2022, what we know is that the host galaxies range from starburst and nearly quiescent. There seems to be no distinction between the hosts of the repeating FRBs so far and the one-off FRBs. And the only thing you can say is that galaxies which preferentially host long gamma ray bursts are less likely to be the common FRB hosts. So that's the main conclusion from that paper. So what else do we know from these associations? Well, we know the host galaxies and the non-repeaters are more massive and have older stellar populations than the original repeater FRB 121102. Two of these FRBs have similar locations in their spiral host galaxies. The host galaxies range from starburst and nearly quiescent, as I said. The physical offsets from the centers range from around 0.6 to 11 kiloparsecs. Here we've excluded a very interesting fast radio burst that's been localized to a globular cluster in M81, which may be a completely different beast altogether. And the offsets are consistent with, oops, sorry about that, short GRBs or core collapse or type 1a supernovae. And as I said, they disfavor the long GRBs. So far, 2 and maybe 3 fast radio bursts have shown associated persistent radio emission. So that could be interesting from the point of view of what we were saying before about whether there's a distinction, whether these objects are young or whether they're associated with shocks and those sorts of things. And so far, the premier or most popular model is magnetars formed in some way are still consistent with all of these offsets and these properties. So these magnetars are these extremely highly magnetized neutron stars. So on to our own project, MeerTRAP, which is also running at the MeerKAT telescope. It's a European Research Council funded project, at least for another week. It's fully commensal, so we don't have any control over where the telescope is pointed. We piggyback on all the MeerKAT large survey proposals. So we in fact piggyback on the observations that Rob was mentioning. This allows us a large sky coverage, multiple visits to the same field to search for repeating bursts, and gives us a whole variable cadence of observations. And we also have a project where we work with the Meerlicht telescope to do optical co-pointing during the nighttime observations. This project wouldn't have been possible without lots of assistance, and I particularly highlight Thundercat helping on the imaging side, and after the fourth collaboration who've been helping us with the optical follow-up work. So we have two different observing modes. We have the flexibility to form coherent beams. So Rob mentioned beaming beams before. It's effectively, you can think of it as many pixels on the sky, each an independent field of view. And we can put up to 768 of these on the sky. That is a very sensitive mode of operation, but has a relatively small field of view. We can also add the dishes incoherently. This gives us a much larger field of view, but a relatively lower sensitivity. And then in combination with this, we have our transient buffer, which is able to store the data from the 64 dishes for up to around about 60 seconds or so, and can be used to form images offline. Skip over that given the time. So just because I believe there was some interest in finding out how the system actually works, here is a cluster located in the Ruhr Array processor building out in the desert with the MeerTRAP telescope. It consists of relatively, well, they were at the time beefy compute nodes, and this is our pipeline. So it's a GPU-based pipeline. We take in data from something called FBFUs, which forms those beams on the sky. Those are fed into a ring buffer, and each of our nodes can take up to 12 beams, and those are passed through some the real-time analysis software. So we don't keep any data apart from when we think we've seen something interesting in the data. It's passed to a real-time machine learning classifier, and then those candidates are saved. So the real-time machine learning classifier, which we call FRBID, was developed by Zafira Hosseini, a former PhD student of mine, and Matt Malenta, former PDRA and software engineer. The system is based on, you feed it these two plots in the lower left. So one's called the so-called DMT plane, which shows you the signal to noise as a function of dispersion, measure, and time. And then the dynamic spectrum, or the frequency versus time plot. And it's a CNN-based classifier, so it takes in both of these images and passes it through the training, and generates either a score between 0 and 1 to give you an idea whether the transient is believed to be a real fast radio burst or not. So this runs in real time, as I say, so we have on the left-hand side here, we have our hardware. Shown here is the so-called FBFU's beam-forming head node. If we see something that we believe is a real event, we generate a VO event. We put that out onto the broker. FBFUs grabs it from the broker, and then freezes the ring. Well, it doesn't freeze the ring buffer, but it starts to write out a chunk of the ring buffer to disk. Should note that this is a huge amount of data, and so what we do is we actually extract a small piece around the dispersion delay of the burst, because the dispersion measures we're searching out to can be many, up to 5,000, and so that can be many seconds of data, and we just can't afford to write out that much data. We hope eventually to make these VO events public. Currently, the false positive rate is still a little bit too high for that. As I already mentioned about MeerLicht, so the dispersion delay that I just alluded to raises a bit of an issue in terms of doing multi-wavelength observations of these fast radio bursts. And that is mainly because, of course, the radio arrives last out of all of these things. And so ideally, what you want is to be able to do co-pointing, and that's what MeerLicht offers us by following along with MeerKAT as it points across the sky. So just to show a couple of highlights, recent highlights from our project. So This is fast radio burst number 8. It's just an internal numbering scheme. It will get an official number when we submit it to the TNS. And here you can see that we've localized the fast radio burst to this ellipse. And within that ellipse, there are two 25th magnitude galaxies. And we're currently just awaiting spectra to be able to confirm which of those galaxies is most likely to be the host. We have another fast radio burst, which is actually in one of the fields that Rob was talking about earlier. It's near GX339, so seen basically through or just under the galactic plane. It was very, very bright source, which meant that we were able to detect it in the imaging data with Thundercat. So we worked with Thundercat on this. So in the 8-second image, despite the fact that this burst was only a few milliseconds long, it was bright enough that you could still actually detect it in the 8-second image. And so we're able to localize this to sub-arc second precision. And we also found that there was some radio emission down below, which is probably associated with the host galaxy. And as you can imagine, for viewing something through the galactic plane, it's very, very difficult and very crowded. But we believe that this faint blob here, which is partially obscured by a star, is the host galaxy of this fast radio burst. And it's consistent with being a star-forming spiral galaxy located at just the right redshift to be the host for this source. So one thing that's quite interesting about this source is that because it's seen through the plane, there's some discrepancy between whether it is the could be right at the edge of our galaxy, in the halo of the galaxy, or it could be actually out at this as part of the normal fast radio burst population. So this is a version of the plot that Rob showed earlier, and these black circles correspond to the luminosity you would expect that you would get for this source if you placed it in the halo or out in the galaxy. And if you placed it in the halo, it would be amongst the brightest bursts seen from any galactic neutron star. And so we think it's much more likely that it's actually a true fast radio burst. Given the time, I'm just going to say quickly about this FRB7. So this was a single pulse source that we detected in our incoherent beam, but again, it was bright enough that we could see it in the imaging that was taken at the same time. And it's actually detected in a field with 2 other known FRBs within 1 square degree, which is quite interesting, but not statistically significant. Sorry, let's just jump over that. This is the more interesting plot, I think. So here is the optical field. You can see that there are 4 sources here. And so far we've got the redshift of 2 of them. And we believe that this one here, Z equals 0.14, is the host galaxy. But we expected the source to actually be at a much higher redshift. And so this is an interesting example where this one is going to be significantly deviant from the McQuark relation. And so I just wanted to highlight also that we are now triggering. We've got our triggering working. Like I say, there's still a few too many false positives, but this is a fast radio burst with a dispersion measure of around about 800 that we now have our transient buffer data for. And so this is a very high DM burst. We'll be able to localize and then hopefully find the host galaxy and get the spectrum and the redshift. So in terms of multi-wavelength stuff, I already mentioned about the optical. The other approach that you can take is to do simultaneous observations or pre-planned simultaneous observations. So we've done some of these with the DWF collaboration in the past. Not been lucky enough to have an FRB go off while that happens. We also undertook a campaign whose main scientific goal was to look for this persistent radio emission, but we also did look for fast radio bursts at the same time, new fast radio bursts at the same time. And we had Meerkat, Hess, and Swift all co-observing with us at the same time. Unfortunately, no FRBs went off again. But we did potentially detect some persistent radio emission, and this is really very interesting because it's important for understanding where these fast radio bursts are born and what the progenitors actually are. So just to summarize, finding fast radio bursts is happening at many telescopes around the world. There are lots of interesting data science, machine learning, triggering, and follow-up problems to be considered. There's lots of exciting science to be done on progenitors, host galaxies, intergalactic medium, circumgalactic medium, missing baryons, etc. There's potential for probes of reionization epochs as well as these other studies, and there's currently very strong interest in lens bursts. And I should point out, we're now starting to probe FRB host galaxies at Z greater than or equal to 1. And although we can't localize this particular burst, we have already found bursts up to dispersion measures of 2500, which would predict redshifts greater than 2. And so soon we'll be detecting those sorts of systems with our transient buffer and also be able to localize them and get host galaxies. Okay, thank you very much. I'll stop there.